Hello and good morning, everyone. Welcome to the class. In today's class, we'll be going ahead and doing some problems based on the concept of potential energy. In the previous class, as you know, we had discussed the concept of potential energy. Basically, two types of potential energies we have to deal with in this particular session, in this particular class, class 11, gravitational potential energy and elastic or spring potential energy. With one more energy that will come, that will be in the next class, next year, not one, two, magnetic energy and electrostatic potential energy. We'll be dealing with those energies in standard 12th. Right now, we are only concerned with two, and those two are number one, gravitational potential energy, number two, elastic potential energy. And we had solved some problems, so we'll go ahead and do one or two more problems on the same concept, and I hope that you are able to solve some simple questions that I'm going to give. So I start with the first question for the day, question number one, and this question is like this. So instead of writing the question, I'll draw the question. So I have we must now get into questions where we will have springs into our discussion. So I have this spring and I have a mass attached to this spring, mass m. The spring constant of this spring is given as k. Now initially, if you can see, this spring, normally natural length is not given, but I'm giving you the natural length. The natural length is x L0, and this spring is extended by an amount x. As you can see, initially the spring is extended by x. Initially, the spring is extended by an amount x. What you have to find out? Number one, the potential energy in the first case, U. If I call this position as a position A, what is the potential energy at position A? That is the first question that I am going to ask. Remember, this block is at rest. So I am holding this block and this block is at rest. This block is at rest. You to first tell me what is the potential energy in this position. Number two, if the spring is further, remember the word further, if the spring is further extended by, if the spring is further extended by an amount x, so x, it is already extended. I'm explaining the question very simply, very slowly, very clearly. You will not get so much time in the real exam to understand the question. If you can do this, this is probably the most difficult question that you can get in the exam. Initially, it is extended by x. Now I'm extending it by x more. So if the spring is further extended by x, find number one, I'll call it A. Find A, the change in potential energy. Number two, work done by the spring. That is the question. Let's see who can do this. What is given to you? Mass of the block, K, spring constant, natural length L0, that is never required. I just gave you so that you understand. X. So I'll just mark what are the things that you know. You know the value of K, you know the spring constant. I am writing it as K. In the question, they might have give you some value for K. You know X, which is the initial extension in the spring. It may be given to you. And the value of mass M is M. So your answer should come in terms of these three quantities. Your time starts now. I'll give you a minute. I hope I am audible and visible and everyone is following me in the online class and offline class. The class people, if you can just send a message that I am audible and visible, that would be good, because right now it looks like I'm talking to a camera and it's not a very good feeling when I'm talking to a camera and no one is watching me. I don't normally do that. So time starts now. A minute. I hope you will be able to solve this question. We have 1 more minute to do it. Simple question. Okay. How are we supposed to do this? Very simple. Let us solve it step by step. Let us look at the solution. I hope you have already done it. How do I solve it? Let us first think about energy in the initial position. Let us call the initial position. It is already given that the initial position is A, so let me call that UA, energy in the initial position. It's very simple. We know the formula. The spring is extended by X. Whether it is extended or it is compressed, spring potential energy is always positive. So we just write the answer, and the answer is plus, always good to write plus, half k x squared. So that is your first answer, as simple as that. Now remember, this is a pretty straightforward question. You might not find a question where they ask you what is the spring energy. Everyone knows that answer. But yeah, the second part of the question could be the question that might come in the examination hall. If the spring is further extended by x, spring is further, remember the word further. So I'm marking out the important words. Further extended by an amount x. What is the change in the stored energy, the elastic potential energy or spring potential energy? Remember, all these energies, potential energies, they are stored. They can be used to do some good work, some useful work. What is the change in internal energy? So now let's draw a simple thing. So now probably what I'm going to draw is on the diagram. Now probably this is at this position. The block has come to position B. I hope you can see this B of mine colored with green. Now probably this block has come to this B position from this original position A, and the distance between A and B is X. As you can see this X, I have drawn an X on the top and colored it green. So now it is further extended by an amount X. I have to find the change in gravitational, not gravitational, spring potential energy. How do I do it? It's very simple. I just write the formula. What is the energy in the final position UB? Now remember, I have to find out the energy in the final position. I have to find out the total extension in the spring. In this case, in this particular case, this total extension becomes 2 times of X, 2X. Remember. So what is the potential energy now? Plus half K into 2X squared. Remember, the total extension is 2X squared. Now this becomes plus half into K into 2X squared, 4X squared. If I cut it down, I will have 2 times Kx squared. That is the final potential energy UB. I hope everyone is following me. Can I have some raised hand that we understand this? From the class, I'm not getting anything. I hope you can see me, can hear me, and you are following what we are doing in the class. I hope everyone is following this. Okay, so I got a raised hand from the class. Great. That is UB. Now the thing is very simple. I have to just find out the value of the change in spring potential energy. That can be very easily done. The change in energy will be equal to final energy, that is UB, minus initial energy, which is UA. We can easily subtract them, get the answer, and stay happy. So you just subtract them and you will get the answer. So it will be 2kx squared, final energy, minus half of kx squared, and our answer would be 3 by 2 kx squared. 3 by 2 kx squared. That is the answer that we were looking at in the first case. The change in gravitational, no. Whenever I say gravitation, just forget the gravitation part. Remember the spring wala part. The change in spring potential energy. Remember, this energy is stored. You can use it for some work. 3 by 2 kx squared. That is the answer that we were looking at. The third part of the question, which is colored in blue, 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 blue. Second was pink, 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 pink. The third part of the question, which is we don't know how to do it straightforward. I have not told you that. What is not required? Why should I tell you a process which is longer to do something which can be done in a shorter way, easier? And that is why I did not tell you how to find out the work done by spring, because I knew that as soon as you understand the concept of potential energy, to find out the work done by the spring will be a cakewalk. That is the cakewalk that we are going to take now. What is the work done by the spring? So delta W by spring, don't have to stress out. It is negative of change in internal energy. So as simple as that. That is the definition of internal energy, or not internal energy, potential energy. That is the definition of potential energy. We just use that definition in W, put the values, and then stay happy. So the answer for this part will be minus 3 by 2 kx squared. These are the answers that we were looking at. Can I have some raised hand that we understand this? Work done by the spring is negative of change in internal energy, negative of change in gravitational potential energy, and here it was not gravitation, here was elastic potential energy, just called potential energy, minus 3 by 2 kx square. I'll give you a minute to note down, and then we will move further ahead in life. If there's anything that you want to ask, please go ahead. I hope we have noted down the solution. I think that is good enough for us to move ahead and move on to a different category of questions. And what is that different category of questions? So we'll add a heading: work done, how to find out work done, how to find out work done. Oh, it should be the other way around. Oh, you can write it that way. Okay. Okay. You can write it that way. You can find change in internal energy from work done, or vice versa. How you can find change in internal energy or work done if a question comes. What you got to do? We have done this many times before. I'll just revisit it. We know that change in internal energy is negative of work done. So if you know work done, you can calculate change in internal energy. If you know the change in internal energy, you can calculate work done. Okay. And you can calculate this by integral of f dot dr taken from position r1 to r2. We all know this very clearly. We'll solve a question on this. This question has been done previously also, but in the previous part we were only calculating the work done. Here we are also calculating the change in internal energy. So we'll solve a question on that. Here comes the question. Question number 1. A force is given in this fashion. It is 2x plus 3. This is a one-dimensional force. Or along the x-axis, I could make a question of three-dimensional force that will not come to you ever. So force is 2x plus 3. This force is displacing the particle. This force displaces a particle or a body from origin. So initial point is origin to x equal to 2. Find number 1, work done by the force. Number 2, the change in internal energy. Your time starts now. Let's see who can do this. I will give you a minute to win it, and I'll wait for your answers. Simple question, should not take much time. Well, I hope you have already solved the question. I'll still give you one more minute. So, one more minute. Okay, so how we got to do this? It's pretty damn simple. We just find out the work done. Work done is integral of f. So f is 2x plus 3 into dr. You can write dx because it is only moving along x. dx, 2x plus 3 dx. It has to be integrated from the point. Initial point is origin. So I write O here, O or 0. Initial point, the origin, O or 0. To the final point, which I will just color by green, x is equal to 2. So here it is, x is equal to 2, and I have made it green. As simple as that. What next? So this is integral. I can integrate it separately. 2x dx from 0 to 2 plus integral of 3 dx from 0 to 2. You should be able to find out the integral. It is a pretty straightforward integral. You should be able to know this. So integral of this thing will become 2 times x squared by 2. If you don't remember it, you can watch the class on integral. That will help you out. From 0 to 2, I can cancel out this 2. Tongue. This is done. Okay. Plus, oops, wrong color. Plus 3 will come out. Integral of dx is simply x. So it will be 3 times x integral from 0 to 2. I can put the values. When x is 0, nothing happens. It's all 0. I put the value of x as 2. Is 2 squared. 2 squared is 4 plus 3 times. When x is 2, it is 2. X into 2 into 3 is 6. So it will be 6. The answer will be 10 units. So that is the work done by this force. Can I have some raise hand that we have understood this? It's a simple integral. Once I have created the integral, that problem is not for physics, the problem is for maths. I know that you are weak in maths. In bio, you may not be so good in maths, but it's a simple integral that can be solved. Can I have some raise hand that everything is fine in the universe? That we understand this, how I've done this? Okay. Now, the next part is pretty damn simple. We have already done the yellow part. Yellow part is the work done. Yellow part is the work done. And we have got the answer to the yellow part. That is simply 10 units. Now we move on to the blue one. The blue question is simple. What is the change in internal energy? And everyone knows now how to calculate the change in internal energy. Change in internal energy is nothing but negative of the work done. So the answer is pretty straightforward. It would be minus 10 units. Remember to keep the same units. If it is in SI system, try to follow it. The answer should be in SI system. Convert everything into SI system. If it's in CGS, follow the CGS principle. Follow the CGS unit. This is as simple as that. I'll give you a minute to go through this question. I hope everyone was able to do this. A minute. Oops. Okay. So we have calculated the change in internal energy from work done. Just find out the work done and do the negative of that. We will get the change in internal energy. Now we move on to the next type of problem that can come, and those type of problems can be like this. They can ask you the force, find force from energy, to find force from energy. If you are given an energy function, how you are going to calculate force from that energy function? Now this is basically maths. This has got nothing to do with physics. This is basically maths. I know that you might not be that good with maths, but I have to tell you that. So how do I find force from an energy function? I'll just give you the formula, and then probably I'll solve a question and think that is good enough for you, because I'll just not go further. So just note this formula down. F vectorly is minus of, I'm going to write something which might sound Hebrew that you don't know, del u by del x IH plus del u by del y j hat plus del u by del z k hat. Now this del, we have seen derivatives. We have seen derivatives. This del is known as the partial derivative. This del, wherever you see this del, del, this del is known as partial derivative. This del is known as the partial derivative. This del is known as the partial derivative. This is one way of writing it. What is partial derivative? Hold on, I'll tell you. This is one way of writing this. Let us restrict ourselves with this one way, because the other way will look just too much complicated for you. Because it's pure maths, it's got nothing to do with physics. Partial derivative. Now, what do you mean by this partial derivative? So, I'll just show you that instead of writing the entire thing, it would be easier for me to show the notes, and probably that will save some time, and you can use that time to note down what is given. So here it comes on your screen right now. This is a screenshot taken from your notes. Force vectorly is minus. I have written del like this, and they have written it like this. So don't write it like this. Write it like this. Del. It's a Greek alphabet. Delta. Del. So F is minus of del u by del x I plus del u by del by j plus del u by del z k. And what is this del u by del x? Just write it as del u by del x. Okay, don't write d, because d will confuse you. Del u by del x. This is del u by del y, and the last thing is del u by del z. Del u by del x is the partial derivative of u. U means energy with respect to x, keeping y and z constant. So y and z don't change. The only thing that changes is x. That is del u by del x. Similarly, what is del u by del y? Partial derivative of u with respect to y. Partial derivative of u with respect to y. Keeping what? Keeping x and z, the other two things, constant. So far, so good. What is del u by del z, which is the third part? Now you can just put it similarly. Partial derivative of u with respect to z, keeping x and y constant. Just write it this way. I try to explain. This will hardly come in your exam, but I'll tell you how to do it. A minute, and I'll wait for you. I hope you have noted it down. How to find out force from energy function. I will not give you a three-dimensional thing. I will not give you function of x and y because you will never get it in your examination hall. So I don't want you to get stressed. What I'll do is I'll give you a simple example that is more likely to come. Even that example is not likely to come. This is purely maths, not physics. So it's very unlikely that this type of question can come, but you should know if it comes how to do it. So I'll give you a question. See if you can do this. The energy, the potential energy of a body is given by this function x squared minus 2x plus 3. X squared minus 2x plus 3. This is how the energy of a body is defined in some conservative field. What field is that? We don't know. But we do know that it is a conservative field. It is a conservative field which gives rise to conservative force. Conservative field, conservative force. So this is the energy. This is how we find out the energy. Find out the force acting on the particle. The energy function is given to you. To find out the force. The time starts now. A minute, 2 minutes. Well, I hope you have already solved the problem. How are we supposed to do this? We just have to put the formula. Remember, there is no y and z here, so the force will only be along x. So we'll just find the derivative and we get the answers done. So how do I find the force? It's very simple. I just put the formula. F vector is will be equal to minus del u by del x, and there's only I here because there is only x here. There is no y, don't have to worry about y. There is no z, don't have to worry about z. Am I clear? Can I have some raise hand that we understand this? From the class, from the online class, from the offline class, do I have some agreement here? Do I see agreement that I just need to find the derivative? Just need to find the derivative. That's it. In the previous case, we had to find the integral. In this case, we had to find the derivative. So both are related to each other. In first case, we found out energy from force. Force was given. From force, we calculated work done. We got energy. Force was given. We found out energy. Integration. Energy is given. We find out force. Differentiation. Integration, differentiation. Integration, differentiation. Ulta सीधा. Just find the derivative and we are done. So f vector will be negative. I put negative d by dx or del by dx of, just have to find a derivative of this thing, x square minus 2x plus 3, and it will be along I hat. Just find the derivative. So minus, what is the derivative of x squared? It is 2x minus 2x. What is the derivative of minus 2x? It is minus 2. What is the derivative of 3? It is 0. I multiply it by negative sign. So what do I have? I have minus 2x plus 2 times I, and that is the answer that we were looking for. As simple as that. It does not get any simpler. Can I have some raise hand that we understand this? I give you a minute to note it down. If you have any doubts, you can ask. Else we'll move further ahead in our life. Well, we are done with these two cases. In case number 1, what we had calculated, instead of writing it like this, I can just write it like this. Find out, I'm just rubbing it out. So I'm changing the heading now. Find out energy from force. If force is given, how do you find out energy? You integrate force. Oops, it's not looking good, so I'll just color it. This one looks good. You just integrate force f dot dr with a negative integral f dot dr, and that lands you with the change in internal energy. Twing, twing. Force is given. To calculate change in internal energy, integrate, and that is how you get energy, change in energy or energy from force. From force to energy, integrate. As simple as that. Number 1. Number 2 is what we have done now, just now. I hope you have noted this down. How to calculate change in internal energy from force, you integrate. Number 2. To find force from energy, force is here, tung tung tung, from energy is here, tung, one time here, and one time here. To find force from energy, you simply differentiate. You simply differentiate. Integral is the reverse of differentiation. Differentiation is the ulta of integral. So that is how the relationship between these two has been and will always remain. The next heading would be this one. So I hope you have noted this down. And the next heading will be based on your notes that are already given to you. Oops, what I have done here. I have done something wrong. Don't worry, I'll just rectify it. Mistakes happen in life. Okay, so what I am supposed to do? I am supposed to share my screen. So I do that now. And it looks like this. Now. The next thing, which is more likely to come in your examination hall, because if you know it, you know it. You don't know it, you don't know it. Potential energy curve, and this is one thing that might come in your exam because they are more likely to give question on curves and graphs than numerical question. Your paper that's made for NEET or for JEE Main or for advanced, it's a balanced paper. It has all types of questions, graphical questions, numerical, theoretical. It's a mix of everything. So you should be concentrating on all types of questions that can come. Potential energy curve. So what has been done here? As you can see, potential energy is plotted along y-axis ux. As you can see, I mean, if you want, I can just tung tung. You can just magnify it so that you can see it on your screen and it looks bigger. Ux. So I have plotted energy on the y-axis and I've plotted position along the x-axis. This is done for a one-dimensional force. That is why you only have ux and x. If the three-dimensional force, you will have three diagrams like this. First diagram between ux and x, uy, or u and y, u and z. So you have three different diagrams. That question will not come because just too complicated to come in a JEE advanced, even not even come in advanced. So they are more likely to see a question like this. Energy plotted along y-axis, position plotted along x-axis. The graph looks like this. And we know to find out force from energy, we differentiate. This is the graph that you will draw. Your time starts now. Draw anything random. Now look at these points B and point C. And we'll discuss more about these points and this graph in the next class. Draw this graph correctly. Point A is somewhere here. Point B is on the tip, on the lower side, or you can call the bottom. Point C is on the tip on the higher side. And here also point D is also on one of the tips. Graph between energy and X. I'll give you a minute to draw it. I hope you are drawing the graph. The graph is still there. You can still draw it. Just try to explain what is given here. So what is here? A graph plotted between the potential energy of a particle and its displacement. It should not be displacement, and its position. So I'll just write it as position. And its position from the center of the force is called, you can just neglect this. It's called potential energy curve. This graph shows the value of potential energy for one-dimensional motion. We know that the negative gradient of the potential energy gives force So minus du, they have written du, it is not du, you should write it like minus del u by del x. It's only a one-dimensional force, so that will be equal to your force. That is what we have done. Please note it down. And you will have the potential energy curve. You note down from here to here. I'll give you a minute. You have to draw this diagram. This is the potential energy curve for energy between position x. Note this down. We will be discussing the other points in the next class because we'll have to finish the entire points in that class. If I do one part here and the other part in the next class, it will be of no use. So just note this down and I'll give you a small task. If you can do it at home, that would be an added advantage. I'll give you a minute. Well, I hope you have noted down this potential energy curve. After this potential energy curve, what we are going to discuss in the next class is the nature of forces. Where is the force attractive? Where is the force repulsive? Where is the force zero? We'll be discussing all these points in the next class. So what I can ask you is if you can note this thing down in your notebook before coming to class tomorrow, day after tomorrow, whenever you use class, it would be an added advantage. We would be utilizing and not wasting time. If you can write these things, you may not understand it, but you can also understand it. It is not rocket science. You can understand them as well. If you can note this down in your notebooks, day after tomorrow, we will be saving a lot of time. Also, in the next page, I think you already have the hard copy of this. On the next page, you have types of equilibrium. Again, you will have to write this entire thing in the next class. If you can do it, if you can draw this table, stable, and if you can draw this table, TABLE, table of stable, unstable, and neutral forces, neutral equilibrium, that will again save a lot of time. So it's, as you can see, it's a big table which explains everything about these equilibrium. So if you can note down this table, as you can see, this entire table, it will save lot of time. So what I am asking you is to write the notes in the first page and the second page up till this position. If you can write it, it would save a lot of time in the next class. I'll wind up today's class here on this note. I hope you have enjoyed the class and understood the concept of finding out potential energy from force, or finding out force from potential energy. That was the purpose of this class, and we have done the purpose. We have completed the purpose. So I am going to wind up this class today. See you in the next class. If you have any doubt, well, I'm always there, and you know how to find me. So, finishing of the class. Have a nice day.